For the last example in this section, we're going to look at computing this area. It says compute the area of the regions bounded by the curves f of x equals x cubed minus x and g of x equals x. And here we have a graph, so we know that f looks like this cubic and then g looks like this nice straight line. And what we're trying to do is we want this shaded area. So we want the area of the regions that are actually bounded by those curves. So here's what we need. We need to first figure out what our integral bounds are, and then we can worry about integrating. Now, notice that this example is slightly complicated for two reasons. So one is that the function that's on top changes depending on which side of this picture you look at. So here, f is bigger than g, but then if you look on the right side of this picture, g is bigger than f. So that means we're going to have to split this into two separate integrals. So maybe let's call this first x value x equals a, and then I'll call this x equals b, and then I'll call this x point x equals c. So notice that between a and b, f is the bigger function. So that means that if we want to compute this area, we would integrate from a to b, and we would integrate f minus g, because there f is the upper function. But then if I want the second area, this area over here on the right side, there g is the upper function. So for that region, I would integrate from b to c, and on that region, g is the upper function, so that would be g minus f. So that's the basic setup. You have to be careful to only integrate on these specific regions where either f is the bigger function or g is the bigger function, and you have to take the bigger function minus the smaller function on each of those regions. So you may need multiple integrals to solve a problem like this. But the point is that you just split up each of the integrals depending on which function dominates in a given region. So I'm going to break this up into two regions because on the left region, f is the bigger function, and on the right region, g is the bigger function. So all that's left now to do before we can integrate is I need to figure out a, b, and c. And notice that these are the x-coordinates, a, b, and c, where these curves intersect. So I'm looking for these intersection points. So in order to find those intersection points, what I can do is what we did in the previous problem. So I want to know the x value where we get an intersection, and to find an intersection, I just set the curves equal to each other. So to find intersection points, we're just going to set f of x equals g of x, and then we'll solve that equation. And whatever solutions we get for x, those are going to be the three solutions that we'll have, or the three intersections that we'll have in the curve above. So we will set f of x, which is x cubed minus x, equal to g of x, which was just x. And now I want to solve this equation. Now this equation will have multiple solutions because it's this polynomial equation that's nonlinear. So I can solve this in a few different ways, but the way that I would do it is I would move everything over to the left side and then try factoring the polynomial. So I would rewrite this as x cubed minus 2x equals 0. The reason that I like writing it in this way is because now we're just looking for the roots of this polynomial. So I just want to know when x cubed minus 2x is equal to 0. And for that, we can use that factoring trick that we've been using. So notice that these have a common factor of x. So I can factor out an x, and then I would get x times x squared minus 2 equals 0. So now, if I know that x times x squared minus 2 equals 0, then that means that either this number is 0 or this number is 0. Those are the only options. So if one number times another number equals 0, then one of those two numbers at least has to be 0. So that means that either x equals 0 or x squared minus 2 equals 0. So x equals 0 is a valid option, and that's going to be the middle option here. So you can see that this b value that we have in the middle here is going to correspond to x equals 0. So those curves clearly intersect at the origin, and that's our x equals 0 intersection. But there are two other x values that we're going to get from this second equation here. So let's solve that second equation for x. So I would probably just add 2 to both sides. That would tell you that x squared is equal to a positive 2. And then if you take the square root on both sides, you'll get that x can be either plus or minus the square root of 2. So these are the three solutions that we get for the intersection points. So if we want, we can go back up to the diagram that we had at the beginning, and we can say that a is, we can say that a is equal to negative root 2, b is equal to 0, and c is equal to positive root 2 in that diagram. So we just found the x coordinates where those two curves intersect, and the leftmost one over here has to be negative 2, and then this one will be the one in the middle, which is 0, and then the value for x over here on the far right intersection will be a positive square root of 2. So now we know our integral bounds. We can just plug those into the integrals and integrate. And I'll do that on the next page because we're running out of room here. So what we just found is that the area is equal to, for the left region, we would integrate from negative root 2 to 0. And there f was the upper function, so that would be an f minus g. And then the right region went from x equals 0 to x equals root 2. And there g was the upper function. So this is the set of integrals that we want to compute. And now I'll just plug in what f and g are. So f was x cubed minus x, and g was just x. So that's our first integral. And then for the second integral, it's going to be similar. This one goes from 0 to root 2 because that's the right region. And this one was x minus f, so that would be, g minus f, but g is just x, and f was x cubed minus x. So this is g minus f. And you can integrate immediately. I would recommend just trying to clean up the integrals a little bit. Really, I should say the integrands. So on the inside of the first set of parentheses here, we have an x cubed minus an x minus another x. So that would be x cubed minus 2x. So that's what we'll integrate for that first integral. For the second integral, we have an x minus an x cubed minus another x, except that this minus sign out front needs to distribute. So if we distribute that minus sign, then that second x would be positive as well. So we would get a 2x minus an x cubed if we simplify the inside of that second set of parentheses. So now we have simplified integrands, and we can just worry about integrating. So now we'll integrate. To integrate x cubed, that would become an x to the 4th divided by the new power, which is 4. Because to integrate a power of x, you just add 1 to the power and then divide by the new power. And then we'll have a minus the antiderivative of 2x. We know that the antiderivative of 2x is x squared. So, and you can also get that, again, by just promoting the power to a 2 and then dividing by the new power. That would just cancel with the coefficient out front, which is a 2. So either way, you end up getting this for the first integral, and that first integral should be evaluated from negative root 2 to 0. And then for the second integral, we want the antiderivative of 2x, which again is x squared, minus the antiderivative of x cubed, which is x to the 4th over 4. That's the antiderivative for that second integral, which we want to evaluate from the 0 to root 2. So now we're in the evaluation phase. We just need to plug in the integral bounds and then try simplifying everything. So for this first one, I'm going to plug in the upper bound, which would give me 0 to the 4th over 4 minus a 0 squared, minus the evaluation at the lower bound. So the evaluation at the lower bound would be a negative root 2 to the 4th power divided by 4 minus a negative root 2 squared, if we just plug in x equals negative root 2 into that first antiderivative. So there's the evaluation for that first term, and then we'll have plus the evaluation for the second term. To evaluate the second term, I plug in the upper bound, so that would be a square root of 2 squared minus a square root of 2 to the 4th power over 4. There's the evaluation for the upper bound, minus the evaluation for the lower bound, which would be a 0 squared minus a 0 to the 4th over 4. Now these we can clean up quite a bit, so notice that these two terms are just 0, so we can just ignore those if we want to. And then for this first set of parentheses, we'll have a negative. Now the negative power, well, I should say any negative to the 4th power will end up being positive. So this first expression will just be a positive root 2 to the 4th power. The square root of 2 to the 4th power is just 4. So that will end up being a 4 over 4 when we simplify, minus negative root 2 squared is just a positive 2. So we'll get that. And then for this second set of parentheses, again, this term over here is a 0, so I'm going to ignore that. And for the first term, what we have is a root 2 squared, which is 2, minus a root 2 to the 4th power. The square root of 2 to the 4th power is just 4. So that would be 4 over 4 again. Now we can simplify this a little bit. This is a negative, that's a 1 minus 2 on the inside of the parentheses. So that would be a negative negative 1 plus, and then this second integral is going to give us a 2 minus a 1, which is a 1. So that's a 1 plus 1, which is 2. So I don't know if you expected the answer to be that simple, but the answer is just 2. So there is a sort of sanity check that you can use in these problems. Remember that these two numbers are supposed to be representing the areas for each of the regions that we talked about at the beginning. So we had a picture that looked roughly like this, where f was the upper function in this region, and then g is the linear function. So we split into two integrals because on this side we had f as the upper function, and then on this side we had g as the upper function. So that's why we need to break into these two separate integrals, but notice that these two terms, this term and this term, are supposed to be giving me the areas of each of these lobes. And therefore they need to be positive. So what we ended up getting here was a positive 1 plus a positive 1. If you end up doing an area integral like this and you end up getting a negative answer, that probably means that you swapped f and g. In other words, that you put the lower function accidentally on top, or accidentally as your first term. And usually the way to correct that is just to flip the sign again. So if you end up getting negative areas in these kinds of problems, it probably just means that you chose the wrong function as your top function. And that's it for this section. So this is the last section that'll be covered on the exam at the end of this week. I'll try to hold an office hour sometime in the middle of this week so that you can ask some questions about it.